Okay, some folks were still having an issue identifying what ions are going to be left in a solution after a precipitation reaction occurs. So we're going to walk through one example problem and hopefully clarify any questions you guys might have about this. So here's our situation for this problem. We're taking 60 milliliters of a potassium iodide solution, and we're combining it with 20 milliliters of a lead nitrate solution. And the first question we have is how many grams of the solid will precipitate? Okay, so before we can even begin to answer that question, we first have to figure out what the precipitate is going to be. So we write out our balanced precipitation reaction. Notice that I included cross-charging when I was writing the solid formula, and then I paid attention to the balancing too. Okay, so a lot of times people will get this part wrong and it will kind of throw off the rest of the problem. So this is really important. Pay attention to that cross-charging. There's a 2 right here. That came from the lead, so I know I have a 2 charge on the lead, which is what crossed down there. Okay? Alright, now that we've got it balanced, I could use my solubility flow chart to figure out that this was going to be the solid. The next thing I want to do is, just like a limiting reactant problem, I'm going to start with the given amount of both of my reactants, solve for the same amount of the solid product, solve for the same solid product, and figure out which amount is smaller. Okay, so here's my volume and the molarity of the Ki solution. Multiplying those together get me into the moles of Ki. At this point, I want to compare moles of Ki to moles of solid produced, so that's the ratio I want to use. Okay, so it's a 1:2 ratio. And then because it's asking about mass, I have to get my final answer into grams of solid, so I'm multiplying by molar mass. Okay. Same thing down here. Now I'm doing the same exact thing, but I'm starting with the other reactant and multiplying by its molarity to get to moles, and then I use the ratio between the reactant and the solid, and the molar mass gets me this answer here. So comparing these two answers, I see that the smaller amount is how much can actually be made. Okay, so this actually gives us 2 bits of information. First is how much the solid precipitate will form, and we can look back at what made that smaller amount, and it's Ki. So that's a really important piece of information because now we know that potassium iodide is the limiting reactant. Okay, so this is really important information to keep in mind for the next part of the question. So the next part of the question is, what are the concentrations of ions remaining in the solution after the reaction is complete? Okay, so I want to remind you guys a couple things. Okay, the solid is PbI2. All right, we just learned that potassium iodide is the limiting reactant. So by definition, this is going to run out first. The Ki is going to run out first. It's going to stop the reaction from happening. So the next thing we want to do is look at what part of the limiting reactant ends up in the solid, and it is the iodine. Okay, so what that tells us is that all of the iodine that we start with in the limiting reactant is going to end up in the solid. So none of the iodine is going to be floating around after the solution is, or after the reaction is over. Okay. The other thing we need to take note of is the other ion that makes up the solid. So in this case, it's the lead. The lead came from the excess reactant. So by definition, excess means you have extra of it. So we will have some extra of the lead floating around after the reaction stops, okay? Because the thing that controls it is not how much lead there is, it's how much iodine there is. So once we run out of iodine, we stop our reaction. So now we know for sure that there's going to be no iodine floating around. There's going to be a little bit of lead floating around. And as you can see here, this other product is aqueous, meaning we have K plus and NO3 minus ions floating around, not actually bonded together, so those will definitely be floating around too. And if you notice, both of these starting amounts were aqueous, so really, essentially they're doing nothing in solution, and so those will be pretty easy to figure out. So I like to do the easy ones first. To figure out the K plus solution, again, this is not going to be part of the solid, so what you want to do is start with the given volume of the solution containing the potassium, so this one here, multiply by the molarity, and then if you've got 1 mole of the Ki, that you also have 1 mole of the K plus ion. It's a 1-to-1 ratio within the formula. So multiplying all this out, that tells us how many moles of potassium we've added. And then to get it to concentration, we have to divide by the total volume of both solutions added together. If you guys notice, we have 60 milliliters being combined with 20 milliliters, so 60 plus 20. Once you pour them both together, their volumes are additive, so that's going to be a total of 80 milliliters of solution. And so that's why I'm dividing by 0.08 liters, okay? So that gets me the concentration of potassium. I can do the nitrate as well. This is also not part of the solid. I start with the volume of the solution that contains the nitrate ion, multiply by its molarity, and then for every 1 mole I have of that lead nitrate, I have 2 moles of nitrate. Okay, that's because of that little subscript right there. That's what that means. So it's a 2-to-1 ratio of nitrate inside this formula. So this then tells me how many moles of nitrate I'm working with. And again, I want to divide by the new total volume of both solutions added together, so that gets me the concentration of nitrate ions. Okay, so now I've got 2 of the 3 ions figured out. Now we've got the last one to figure out, and the last one's a little bit more tricky, so we're going to walk through that one. Okay, so I've recopied the reaction up here. Remember that the potassium iodide is our limiting. Okay, so alright, so we're going to find out the Pb2+ ion. And remember, this is coming from the excess reactant, and it made part of the solid. So some of this was already used to make the solid, but some of it will be floating around, and that's the part that we're trying to figure out, is how much is floating around. So the first thing we have to do is figure out how much of the lead ion that we started with. Okay, so that's pretty simple. We start with the volume of the solution containing lead, multiply by its molarity, and then within this compound we have a 1 mole to 1 mole ratio, meaning like every mole of lead nitrate we have 1 mole of lead ion. Okay, so it's 1 to 1, and that tells us how many moles of lead we're starting with. Okay, so now that we know how much we started with, the next thing we need to do is figure out how much actually reacted. Okay, and this is when I want to remind you about the limiting reactant. Because the limiting reactant limits how much product can be made, that tells us how much of the excess is going to actually be used as well. So how much of this we have dictates how much of this we're going to use. So when we go to figure out how much was used, we actually have to start with the given amount of the limiting reactant, okay, multiply by the limiting reactant molarity. And this is the most important ratio. If you guys notice, I'm using the ratio between reactants. I've got a 2 to 1 ratio here, okay? So this 2 and this 1, that's the ratio I'm using because I want to figure out, okay, for every 2 moles of my limiting reactant, I use 1 mole of my excess reactant. So that's what the ratio is right here. So I've got my 2 to 1 ratio right there. And again, that ratio tells me how much of the excess reactant I used when all of the limiting reacted. Okay? Again, we're not concerned about the entire compound though, we're just trying to isolate the lead ion. So we know for every 1 mole of lead ion, every 1 mole of lead nitrate, we have 1 mole of lead ion. And so now this whole system basically got us to how much of the lead ion we used to react with a limiting reactant. Okay? So this basically tells us if we start with this amount of the limiting reactant, we're going to use this much of the lead ion to make our solid. Okay? Alright, so now we know how much we started with and how much we used. Now the only thing left to do is subtract the starting and the use to figure out what's left. Okay, so we do that subtraction. That tells us that we're going to have this much lead floating around in solution after the reaction occurs. And then we take those moles, divide it by the new total volume of the solutions added together, and that gets the concentration of the lead. Okay, so I think a part where people struggle with most is realizing this conversion right here. You always have to start with a given amount and molarity of the limiting reactant, use the ratio between the 2 reactants, and then isolate the ion that you're actually concerned about, and that tells you how much of that ion you used. Okay, so good luck with that. If you guys need any more clarification, let me know.